sharing. We can see it now.
It's okay. Now, I already introduced myself and said that this is mathematics for foundational mathematics for Web3 developers. So what I intend to go through today, then tomorrow, then on Thursday, will be just, I began with the number theory. And that I'll be looking at the basic properties of integers, divisibility test, Euclidian algorithm, the extended Euclidian algorithm, then basis of numbers, then modular arithmetic, and so on. So today we may cover maybe up to number basis if time allows us, or modular arithmetic. Now, I intended to go step by step so that we all get to know what we're talking about, because this being an introduction, it forms a big background of what we'll be covering later. So it's good we understand it, the background well, before we proceed. Now, throughout my course, or throughout this course, we'll meet several symbols, but I've given this 4 or 3. Just a minute. Let me share again. Now, can you see I'm sharing? Yeah?
Yes.
So the symbols that I will be looking at are the ones I've put here. Like this first symbol here means belongs to. Just a minute, my pen is let me position my pen well. Now, these symbols, most of them you are familiar with them. The symbol a member of or belongs to this symbol means it's an element of. For instance, if X, or if A is a member of X, if A is an element of X, then we write it this way. To mean A is a member of X, or A belongs to set X. A set is just a collection of objects. Now, if it's not a member of X, then we write it, we use this symbol here. So for instance, if Y is not a member of this X, or if it does not belong to this X, then I'll write it this way. Now, I'll also be using this symbol here to mean implies. And then the last symbol that I want us to know as we begin is this symbol that looks like a colon. This one I use it to mean such that. And sometimes I can also use this one to mean such that. So in this course, I'll be using this twice. I'll be using it to mean such that, and sometimes I'll be using it to mean divides. For instance, I can say 9 divides 18. 9 divides 18. So that is the 2 ways I'll be using that symbol, but you'll be, as we progress, you'll be knowing what it means. If it means implies, you'll say that, and then if it means division, you also know that. Okay, so just a minute. Now, so I said we begin with the basic properties of integers. And I've said that this will be very important in cryptography and also in blockchain, because cryptography, of course, is very much useful in blockchain. And I've defined on what number theory is. I said that give me the number theory. I've said the number theory is just a set of integers, and this is the set of integers. The set of integers that comprises of all the numbers, the negatives, positives, and zero. So we say that there's a set of integers. We also have a set of the natural numbers, but a set of the natural numbers is a set that comprises of numbers 1, 2, 3, and so on. And we denote it by, we denote that by capital N, the set of the natural numbers. The set of the natural numbers, we denote it by this way. So just a set of numbers 1, 2, 3, and so on. That is a set of natural numbers. But now when we talk about the set of integers, this is what we mean. Now, so what is also important in cryptography as well as blockchain, I've said is what we'll be looking at. What is divisibility? We shall be looking at prime numbers. We shall be looking at the factorization of those prime numbers, and then the greatest common divisors, least common divisors, and so on. So we begin with the divisibility, and I've defined what divisibility is. What do I mean when I say that a number divides another number? So that's what I mean by divisibility. So for instance, if I was to say that 4 divides 8, what do I mean? So for 4 to divide 8, what I mean, if A divides B, then in mathematics, that implies, I said I'm using this sign to mean implies. It implies that you can get another number, which when multiplied by A, you get B. So it means there exists another number, let me call it C, such that this C times A gives you B. That's what I mean by A divides B. For instance, I can say 2 divides 8. And so what this means is that I can get a number 4, which when multiplied by 2 will give me 8. So that's what I mean. So this, I said this symbol, I'll be using it to mean it divides. And also in some cases, when I'm referring to sets, I'll be using it to mean such that. But under divisibility, I'm using it to mean it divides. Now, I can say 3 divides 9. I'm not written this because this one means 9 divided by 3. 9 divided by 3, but this one means divides. 3 can divide 9. Now, again, let me just emphasize, I cannot write this. I cannot say that 4 divides 9 because then by remainder. Whenever I say it divides, it means there's no remainder. For instance, 3 divides 9, there's no remainder. The remainder is 0. The remainder is 0. For this one, this is not true. So if it's not true, then I'll do this. I'll use this symbol to mean 4 does not divide 9. Now, so just I've given some examples here, and these are the examples. For instance, 2 divides 8, 4 divides -20, and the reason is I can get a number of -5, which when multiplied by 4 gives me -20. And I've said 3 does not divide 16. I'm using this symbol here to mean does not divide 16. Now, I've also given some theorems, but I'll not go much into theorems, only that theorems are important for you to understand the mathematics. And the definitions are also important. So in this course, whenever I give a definition and whenever I give a theorem, it's because that theorem or that definition will be very much necessary as we go forward. So the theorem here says, let A, B, and C be integers let A, B, and C be integers. I'd already defined this symbol to mean belongs to. So that means A, B, let A, B, and C belong to the set of integers. Then part A divides A. And at the same part A has, A divides, no, 1 divides A, and also 1 divides 0. No, A divides 0. And then part B, I have, if A divides B, and A divides C, then A will divide the sum of B and C. I'll just use an example before I prove that. An example of this B, part B here. What part B is saying is, if 2 divides a number, for instance, if 2 divides, let me say 6, and then the same 2 divides 8, and then the 2 divides the sum of these 2. 2 divide the sum of these 2. And so, in fact, this theorem, we can also extend it. It means if 2 are to divide a number, if, let me say A divides a number, if A was to divide a number, and then A divides another number again, let me say call that number C, then A would divide anything we do to these 2 numbers. These 2 numbers, if I were to subtract them, A would still divide that difference. In fact, if I was to multiply them again, A would still divide that. So we can generalize this. For instance, let me take 4. 4 divides 20. And then 4 divides, let me say 8. If I was to get the difference between 20 and 8, 4 would still divide that difference. And if I was to multiply these 2, 4 would still divide that product. So whatever we do to what 4 divided, it will still divide this, what we come up with. Now, so I will not go, I will approve this theorem, but I'll leave for you to look at it later. This is my proof. The first one was very easy. It is basic to prove that, what was it? It was to show that A divides itself. And also to show that 1 divides A. And 1 can divide any number. That's what it means. 1 can divide any number. And also A can divide, 0 can be divided by any number. That's what this last part means. So that part 1 is elementary to show that A divides itself. I've said that the reason from the definition of division that we had, we said that for a number to divide another one, for a number to divide B, for A to divide B, it means you can get another number, C, which when multiplied by A gives you B. So when we say that A divides itself, it means we can get a number, and that number is 1, which when multiplied by A, you get A. So this is the proof to that. It's very elementary to prove that. And most of the proofs, they are elementary. We just look at them later. You want to look at especially the application part of that theorem. Now, just before we go to the application, I've also defined what a prime number is and what a composite number is. And I've said that a number will be said, and that number should be positive. That number will be said to be prime if its only divisors are 1 and itself. If its only divisors are 1 and itself, then we say that number is prime. For instance, the smallest prime number is 2. The only numbers that can divide it 2 are 1 and 2 itself. The other prime number is 3. The only number that can divide it are 1 and itself. So that's what we call a prime number. And any number that is not prime shall be called composite number. Composite number. That is a number which we can obtain by multiplying two other numbers. We call it a composite number. And then I've noted there that the prime numbers are infinite. Yes, Cheng, I can see your hand is raised up.
All right. So in a lot of this math, the idea of prime numbers always comes up. Why are prime numbers so important?
Yeah, prime numbers are important, and we will see how important they are as we progress. They're important in so many topics, and so as we progress, we'll be seeing how important they are in each of the topics. I cannot list all the usefulness of prime numbers now, but they're very important, and we'll be seeing how important they are. Is it okay, Cheng? That
Yes. Yes, that's fine.
Thank you. Now, again, what will be very important is we must know that we cannot say which one is the largest prime number, because they are infinite. They are infinite. There are so many prime numbers we cannot count. The fundamental theorem is here, and the fundamental theorem says that every integer that is greater than 1 is either a prime number, or it can be factored uniquely into product of prime numbers. So we are saying that any number that is greater than 1 is not a prime number. Some people confuse it to be prime. It's not. It's not a prime number because it does not satisfy the properties of a prime number. We said a prime number, first of all, has two divisors, 1 and itself. 1 and itself, but 1 has only factor. Has only one factor. It does not even meet these two conditions. Now, so what this fundamental theorem says is any number that is greater than 1, any number that is greater than 1, that number will either be prime, or if it's not prime, then it's composite. It's composite. And it being composite, it means that that number can be factored as a product of prime numbers. We can factor it as a product of prime numbers. That's what it means by composite number. And so what I've showed therefore is how to factor composite numbers, and this we did in high school or in primary, factoring prime number and composite numbers. So just to remind you what I did here, I asked myself how many times does 2 go here, and it went there 378 times. Then I'm only using prime numbers to do this. I'm only using prime numbers. So I used 2 went there this number of times, and then this 2 went here this number of times, and then this 2 went here this number of times, and then this 3, no, this is 3, and then this 3 again, I used 3, and then, so I can say this number therefore can be factored as a product of prime numbers, and that's how I factor it. That I had 2 was there twice, 3 was there 3 times, and 7 was there once. So I factored this as a product of prime numbers. So that is what the fundamental theorem says, that if a number is not prime, then it can be written as a product of prime numbers. And I've done another one here, just used a different way of factoring, and they all mean the same thing. I'm saying I'm using prime numbers, 2 factors, 2 goes into this number of times, Then what about this 2? Goes here 3,150 times. Then, and again, after that, I discovered that I had 3 2s, then I had 2 3s, then I had 2 5s, then I had 1 7. So I have factored this number as a product of the prime numbers. What is the way of factoring numbers using your programs? You can use a program and see how can you factor numbers as a product of prime numbers. So that I've noted that one here, and I've said that note that any algorithm finding prime number factorization of integers will also be answering a simple question of whether a given integer is prime or a composite. What that means is that if you are to come up with an algorithm, my internet is unstable, that's what I'm seeing from this side, but you can still hear me, is that okay?
Yes, we can hear you.
Can you hear me?
Yes.
Yes.
It's okay. So what this statement is saying that if you are to come up with any algorithm, it's okay, thank you. If you are to come up with any algorithm that can be used to factor prime numbers, if you are to come up with an algorithm that can write integers as a product of prime numbers, the way we've done above, then that algorithm will be very important because we can use it to tell if a number is prime or is not prime. For instance, if it doesn't factor a number, then we can say that this number is prime. But if it factors that number as a product of prime numbers, so we can say this number therefore is not prime. Now, so we talked about divisors. We say that we can have a number that divides another. For instance, if I have 8, what are the divisors? What are the divisors of 8? What numbers can divide 8? The numbers that can divide 8 are 1, 2, 4, and 8 itself. So these are the factors of 8, or the divisors. We call them divisors. Divisors of 8, or factors. You can also call them factors of 8. Now we can also have, let's talk about 6. Supposing I have 6, what are the factors of 6? Or the divisors of 6 are 1, 2, 3, and then 6 itself. These are the divisors of 6. Now, these 8 and 6 are 2 numbers. They have factors. And which ones are common factors between these 2? What are the common factors? I can see 1 is common, and then I can see 2 is common, and those are the only common divisors. So we call them common divisors. 1 and 2 are common divisors. Now, what is important for us is the greatest common divisor. Greatest common divisor, the GCD, is the greatest common divisor. So of the common divisors, which are 1 and 2, the greatest is what we are interested in. And that is what is very important in this course, the greatest common divisor. So I've said a common divisor of integers a and b is a positive integer b that divides both the 2 numbers, that divides both of them. I've given an example of 8 and 6, and I've said that 2 is therefore the greatest of the 2 common divisors. An example is here. I will this example, and you'll do it at your own time. Find the GCD of these two numbers. And I've just said the GCD is the greatest divisor. So you have common divisors, and then you pick the greatest of those common divisors that can find the GCD. Now, this term is very important. And again, I'll not go into the proof, but the proof is here. I've said if A and B are integers and D is the GCD, then I'll just show an example. Then, if I were to take the GCD and divide through the numbers, for instance, let me talk of the 6 and 8 that I've talked about above. We found that the GCD of these two numbers was 2. Now, so if I divide these 2 into each of the numbers, if I divide 2 into 6, I'll get 3. And if I divide 2 into 8, I'll get 4. So what this term is saying that the GCD of that will then be 1. That's what this term is saying. That the GCD of those numbers that we get after dividing the GCD, we divide the GCD in each of the numbers, and then you get the new GCD. That new GCD will be 1. That is what this term is saying. And again, we see how to apply this theorem. As I said earlier, much important going forward. Now, I already said that we can get the GCD by, first of all, finding out what are the common factors. And that method is very, very long. So there's an easier method, which we then call the division algorithm. We use the division algorithm, repeated division. So this is a very easy method and it's faster and it has a lot of applications going forward. The use of division algorithm. And then division algorithm then gives birth to Euclidean algorithm, which is also very important going forward. Now, so division algorithm, let me again repeat, it uses repeated division. So we divide, we get the remainder, then again divide and so on until the remainder is 0. That's what we call the division algorithm. So you divide until the remainder is 0. So I've defined the division algorithm here. I've said if A and B are integers and B is greater than 0, then A divided by B has a quotient Q and a remainder R means this. So let me just give an example. Just give an example of what I mean by this definition. Supposing my A is 7, no, my A is 2, and my B, let me call B is 2. Let me say that supposing my B is 2 and my A is 7. What division algorithm says is that 7 can be written as 3 times 2 plus the remainder. So we're asking ourselves, if 2 are going to 7, no. If 2 are going to 7, how many times will it go there? So it goes there 3 times. And then 3 times that will be 6, the remainder is 1. So that means 7 can be written as, this is the divisor. This is the divisor. And 3 is the quotient. 3 is the quotient, and then 1 is the remainder. So 7 can be written in terms of the divisor times the quotient plus the remainder. And in this case, our remainder is 1. This is what division algorithm is all about. That we can write any number in terms of the divisor and the quotient and then plus the remainder. So that's what we'll be doing. And that's what we call a division algorithm. But what is Euclidean algorithm? That's what is important. And we shall see how what Euclidean algorithm is. Now, so we are doing division, we are using the division algorithms subsequently, continuously, until we have a remainder of 0. I've given an example here that 4 can be written as 5 goes there 6 times, and the remainder will be 4. Now, okay, so I've given an example of how to apply division algorithm to get the GCD of 36 and 60. I want to get the GCD of 36 and 60. So I use division algorithm. So what division algorithm says, I take this 60 and divide by 36. So I ask myself, how many times does 36 go there? And 36 go there 1 time. 36 go there 1 time. And the remainder will be 24. Next, I divide this remainder into 36. So I ask myself, the remainder that 24 goes into 36 how many times? And I can see it also goes there once. So when you subtract this, what will be the remainder? The remainder looks like 12, is it? Is the remainder 12? Let me see, 36 minus
Yes.
24 is 12. And then ask myself, what about this remainder? How many times does it go into 24? And so I can see that it goes there twice.
Fine.
Is it? And the remainder is 0. So we have done division algorithm, and I've said we do continuous division until we have a remainder of 0. Once you have a remainder of 0, the GCD becomes the remainder here. This remainder above the last remainder that we had. That was more, this one is 0. So I'm not calling it even a remainder. The last remainder that we had was 12. So this last remainder that we had becomes the GCD of those two numbers. So the GCD, therefore, of 36, of 60 and 36, therefore, is 12. We've used division algorithm, which uses repeated division. I'll take another example just so that you see how to use division algorithm. But I've already explained here. I've already explained the first step. Yes, Felix?
Good evening. Can the Euclidean algorithm be used to find the GCD of more than 2 integers?
Yeah, no, if you come up with a program, but the manually this way is not very easy. Manually, there's another method that we use if it has to be 3 numbers. There's another method that we use if it has to be more than 2 numbers. But
oh, so this one is only applicable
yes,
for 2 numbers.
for 2 numbers. But if you come up with a program, the program, if you're using it, I don't know whether a program can come up and do 3 numbers, but manually we do only the 2 numbers. We're using Euclidean algorithm.
Okay.
Yes. But if there are more than 2 numbers, there's another method we use, and we'll come to that later. If you have to get a GCD of 3 numbers, 4 numbers, and so on. And you see, if there could be more than 3 numbers, what happens? You first of all have to arrange them. You have to arrange them into pairs of 2. Pairs of 2. You do the first 2, get the GCD. Let me just show you an easier way that maybe you can work out. For instance, supposing I have 8, I have 12, and I have, let me say 48, and I want the GCD. Maybe now I would find the GCD of these two. Let me call this GCD D. Once you have this GCD D, now take this D and 48 and find the new GCD. The new GCD of D and 48 would now be the GCD of these three numbers. And I think that is how you can do it. If you have to use Euclidean, maybe that you have to arrange them in pairs. You begin by these two, find the GCD, and then now that GCD combined with this 48, find the new GCD. That will then give you the GCD of these three numbers. That is how you can do it. Maybe you come up with a program and see how you can do that. But you have to, that program then has to combine, first of all, those, you pair them. Or you can begin with this, find the GCD of these two, then that GCD, call it D, now combine with the 8 and find the GCD, because the GCD is a common factor, common divisor. So if it's a common divisor here, then take that common divisor and combine with this, and then now get the new common divisor of those two. But when we are doing a Euclidean algorithm, this division algorithm will just combine two, because you have to do two at once. We've not tried, but that will work. That will work. Is it okay?
Yeah, it's okay.
So you come up with a program and combine those two, then combine two and so on.
Okay.
Now, so I just given the steps here, and I'd say that applied division algorithm to 36 and 36. So what that means, we're asking ourselves, how many times does 36 go into 60? And I've written it in a bracket. I've said it goes there once and the remainder is 24. Then step 2, that remainder, the remainder that we had here, which is 24, how many times does it go into 36? That's what I've written here. And then there's until we have a remainder of 0. We continue until the remainder is 0. And then the GCD becomes the last non-zero remainder. The last non-zero remainder. This was the last non-zero remainder, because this one is 0. So the last non-zero remainder is the GCD. Now, what is Euclidean algorithm? What we've just done is the division algorithm. We've been applying division algorithm. Now, Euclidean algorithm is now the reverse. I've said here to compute the GCD of two numbers by the algorithm is to find this. Okay, that's Euclidean algorithm. What I was explaining is the extended Euclidean algorithm. The reverse is the extended. But the Euclidean algorithm is the process of finding the GCD by using repeated division. But what I was saying, the reverse is something else that we will go to. Now, so use division algorithm, or somebody can say use Euclidean algorithm to compute this GCD. So just asking ourselves, how many times does 756 go to and
Hi, hello, Mr. Sako. Mr. Sako, we're losing you. Maybe kindly retrace back like 3 minutes.
coordinated.
Hello, Dr. Ali.
Hello?
So I think, yeah, just where you're starting on the solution, that's where we've lost you.
Can you hear me?
Yes, we can hear you now.
Yes. But starting on
We lost the solution.
oh, okay, you
All right, let's give Mwalimu a few seconds.
in the as we proceed. Now, this is the division algorithm. This is the division algorithm just before it was extended. This is what it says. I took the first number divided by B, and B went there Q1 times. The remainder was 1. And then I asked myself, what about this remainder of R1? How many times does it going to be? It went there Q2 times, and that is the quotient 2. And then the remainder was R2. So we proceeded until that we had a remainder of 0. So this is the algorithm, the division algorithm that we are using to find the GCD. So the GCD then becomes the last non-zero remainder, which is RK. Now we are at the extended Euclidean algorithm, and I've said that this is process of just making the GCD the subject of the formula. So when we reverse, just give me 1 minute and look for something for a charge, and then I will progress. Just 1 minute.
Can you guys hear me? Can you confirm that which can hear me?
Sorry for
Yes,
that.
Yes.
Okay, yeah, Mwalimu had dropped. Okay, Mwalimu, you're back. Good.
So I'd say the extended Euclidean algorithm, we shall be making the GCD to be the subject of the formula. I just want to go through an example straight. So we want to write the GCD in this format. We want to write the GCD so if we had A and B, we want to find the GCD of A and B, and then write that GCD as a linear combination of A and B. And so what is that process? That process is just reversing. We're just reversing from this last, where we had the last non-zero remainder, which is our GCD. This is what we make the subject of the formula. Then we write it in terms of these two. And then after that, we replace the other remainders as we move up. So we begin from the bottom going up. So we replace all the remainders, substitute all the remainders as we move up. So here I've just shown that calculation as we move. We have said beginning with the second last line of the algorithm, we make the GCD the subject of the formula of that equation. And that GCD was this. So to make it the subject, when you reverse, what you get is I'm going back to the algorithm. When you reverse here, let me just write. So I'm reversing, I'm reversing, I'm going up, but I make this the subject of the formula. So this is RK, and this RK is RK minus 2, then minus QK, RK minus 1. Now this is a remainder. This remainder is here. So we again substitute it. What is its equivalent? Its equivalent is this. It is equivalent is RK minus 3, then minus this. So that instead of this remainder, we write its equivalent. We write its equivalent, which is, we just take the other side of the equal sign. We take it, the other side of the equal sign becomes minus. So let's use an example to make it clear. The question is here. The question says, find the GCD of these two numbers and then express it in this as a product, as a linear combination. Express it as a linear combination. So the first thing I do is to use the Euclidean algorithm. And we've already done that. We're asking ourselves, how many times that does this 364 go here? It goes there twice. And the remainder is this. Then this remainder goes into 364 many times. Because there are 9, and this is that 1 is the remainder. Then 31 into that 7 goes there once, and the remainder is 6. 6 into 31 goes there 5, and the remainder is 1. And so this is the GCD. Once you have this GCD, you now use the extended Euclidean algorithm. And that is what I want to do, because we shall be using it again to find the inverse. Now we make this one the subject of the formula. This one will be the same as that 1 minus, this one crosses the equal sign, becomes 6 minus 6 times that. Now this remainder, we now substitute. We've already done with this remainder. We are already done with that. This remainder is what we have here. Now the next remainder is what we substitute. 6. This 6, we write it is equivalent. So we just make 6 the subject of the formula. So 6 is the same as that 7 minus this. So what we then write is that 1, instead of 6, we write the equivalent, which is that 7 minus that 1 multiplied by 1. Then there's this 5. There's this 5 outside the bracket. What does this give us? So we just expand. 5 goes inside the bracket. Just open the bracket using this 5. So what we then get is that 1, is that 1. Then there's this minus outside here, multiplied by that 7, would be negative that 7. Then there's this 5. Then this minus times this minus will be positive, that 1. Then there's this 5. And there's a 1 here. There's a 1 here. 5 times that 1 will be 5. At this point, we collect the like terms. And the like terms are that 1 and that 1. Let me begin with that negative 37. Multiplied by 5. And then that 1 and that 1 is that 1 multiplied by 6. Where does 6 come from? 6 is here. We just factorizing. This 31 multiplied by 1, and this is plus this 31 multiplied by 5. So when you factorize, what you get is that 1, and what is inside the bracket is 1 plus 5, which gives us this 6. That's how I got that. Now we have substituted this remainder. We are done with this remainder. So the next remainder is that 1. So we write its equivalent. So what we have here is that 7, negative 37, multiplied by 5, then plus that 31, but that one we write its equivalent. Its equivalent is that 7. Is it that? No, it's 364. Just a minute. That is 364. The equivalent of that one is 364 minus that. 364 minus that 7 multiplied by 9. That 7 multiplied by 9. Close the bracket. Then there's this 6. You don't forget the 6 because it was multiplied by that 1. Now at this point, let me just erase some space a bit. We again open the brackets here, open the brackets, but let's begin with this, which is negative 37 multiplied by 5, and then plus, there's this 364, and outside you have 6. Just opening that, opening this bigger bracket. Then there's this negative 37. Inside the bracket, you have 9 and you have 6. The product of that is 54. Now, collecting like terms. First of all, let me write 364 multiplied by 6. And then collecting like terms. This was minus that 7. And this is minus that 7. So what I have there is minus that 7 into 59. So 59, I got it 5, that's just 5 plus this 54. That is what gives me 59. Now substitute the last remainder. The last remainder is that 7. We substitute remainders from bottom going up. So what we get is 364 multiplied by 6, then minus, instead of this that 7, we write the equivalent, which is 765 minus 364 multiplied by 2, then close the bracket, then multiply by this 59. Then again, what we do again is to collect like terms, open the brackets there, and then collect the like terms. Let's open that bracket. Let's begin with this 364 multiplied by 6. Then open the bracket. There's this minus here. So that will be minus 765. Then there's 59 outside. Also use it there. Then this minus that times this minus will be positive. That's 364. Then there's this 2 multiplied by this 559. Is it 118? When you multiply that, it will be 118. Then collect like terms. Let me begin with the negative 765 multiplied by 59. And then these two put together, that will be plus 364. You'll go through the workings and see. And so this one you add, you get 124. Now we can rewrite this one as 765 multiplied by negative 59 plus 364 multiplied by 124. And we say this is equal to 1, because 1 was our GCD. So we've written 1 as a linear combination of the numbers we began with. We began with these two numbers, and we finally add that. So 1 is the same as this, multiplied by this, plus 364 multiplied by 124. So this is what we call the extended Euclidean algorithm. So if somebody, for instance, was to ask me what is the inverse of 124, I'll come to that. But the inverse of a number A would be B if the product of these two gives me 1. That is what we call the inverse. So for instance, in the normal mathematics we do, the inverse of 2 would be a number which multiplied by 2 gives me 1. That is in multiplication. So that is, so for instance, somebody asked me the inverse of 364. I'll be looking at a number that is multiplied by 364 to give me 1. And that is what I call the inverse. But we shall come to that again. And briefly, that is what we do to get the inverse of a number using the extended Euclidean algorithm. Let's look at another example, or before that, I just show you the workings. I typed my workings from here. I said, since 1 is the GCD, apply the extended Euclidean algorithm by first making 1 in the second last equation here, the subject of the equation. Then substitute all the remainders 1 at a time from bottom going up. That's what we've done. So when you do that, this is what you come up with. This is what you come up with. So let's look at another example. Use the Euclidean algorithm to find D, the GCD of these two numbers. Then write D in terms of as a linear combination of 60 and 33. This part we already know how to do it. Once you've done that, the GCD is the last non-zero remainder, which is 3. Then let's make that 3 the subject of the formula. So let's already showed the workings. So what I did was 3, these are 3. I write its equivalent, which is 27 minus 6 multiplied by 6 multiplied by 4. Then now substitute this remainder. It is equivalent when I take this on the other side, is that 3 minus 27 multiplied by 1. So this 27 I write here, then minus this minus. Instead of this 6, I write the equivalent, then times 4. Now let's simplify this part. 27, then minus, this minus multiplied inside the bracket. You have minus 33 times this 4. So you get this. Then again inside the bracket, multiplied by this minus, I have this minus times minus gives me positive 27. Then this negative, this 1 times this 4 gives me 4. Then you collect like terms, this and that. So this first one is the same as 27 multiplied by 1. Because 1 times anything, you get that anything. Then plus 27 multiplied by 4. When you factorize, it will be 27, 1 plus 4, which is 27 multiplied by 5. That's what I wrote. That's what I wrote here. Now, so we had already substituted the remainder, this remainder. Now you substitute the last remainder, 27. And when you do that, 27 will be the same as 60 minus 33. So that's what I have written here. 60 minus 33. Then multiply by this 5. Then when you correct like terms, what you find is that the GCD, which was 3, is the same as 60 times 5 plus that 3 multiplied by -9. Now, you cannot use this one to find the inverse of any number here. This one you cannot use it because when do we say that numbers have inverses? Or that one you'll be looking at a base. So you're looking at what base are we working with. And so numbers, for instance, if you're looking at, if you're working with the base of 10, for instance, the numbers that will have inverses will be numbers which are relatively prime, to 10. Those are numbers which will be having inverses. So, for instance, these numbers are not relatively prime to the base we're working with. So that is why the GCD here was 3. So when you make it the product, when you make it when you make it the subject of the formula, it does not give you the inverse of any number. So you cannot say at -9 is the inverse of that 3. You cannot say that. So for instance, this time the base here is 60. The base is 60, and you can see that 3 and 60 are not relatively prime. That 3 and 60 are not relatively prime. So this that 3 cannot have an inverse in the base of 60. Cannot have an inverse because they are not relatively prime. But we shall come to that later. Now, so I just want to introduce number bases. The bases of numbers, and I'm doing this because we shall also require number bases later. I've introduced and I've said the bases that we normally use, commonly used base, is the decimal. And the decimal is where we are using digits 0 to 9. 0 to 9. So these numbers that have digits 0 to 9, the base is 10. And the computers use the binary system. The binary system uses 0 and 1. So the base is 2. The base is 2. So what I want to do here, I want us to see how to convert from one base to another one. Now, if the base is 7, it means that the numbers will be, the numbers we'll be using are 0, 1, 2, 3, all the way up to 6. If the base is 10, we are using numbers from 0 to 9. If the base is 2, so that means if the base is n, then we'll be using numbers 1, 2, 3, all the way up to n minus 1. So those are the numbers we are using. But what is important is how do you convert from one base to another base? And it's very easy. I've said to convert. I've said to convert. If the base is 10 and we want to convert to another base, the base is 10 and we want to convert to base 7, then we are using division algorithm. We are dividing by 7 and noting the remainder at every point and then writing those remainders. I've begun by converting this number to base 2, convert this decimal number to base 2, to binary. Binary means base 2. So that means I divide this number by 2 and note the remainder. So I ask myself, 2 goes into 53 how many times? Got that 26 times, and the remainder will be 1. What about, what about 2 into 26? So 2 goes into 26 13 times, and the remainder is 0. What about 2 into 13? So 2 goes into 13 6 times, and the remainder is 1. So what about 2 into 6? 2 goes into 6 3 times, and the remainder is 0. What about 2? So we are doing that until whatever we shall be dividing in shall be 0. So what about 2 into 3? 2 goes into 3 once, and the remainder is 1. So what about 2 into 1? So 2 goes into 1, how many times? 0 times. And the remainder is 1. So when we reach there, we stop. Once we say that the quotient, once the quotient is 0, once the quotient is 0, we stop. Then after stopping, we write the remainders from the bottom going up. So the binary number, therefore, is this 1, then this 1, then this 0, then this 1, then this 0, then that 1. So that is the binary number that you get when you convert this decimal number. Now, normally we write it this way. We write the base here. This means this is a decimal number. And the binary number we formed is this. And so we write the base as a subscript. Although it's not a must, but whenever you see a base as a number as a subscript, that it means that is a base. So I'll not go through all the examples, but what is important is if you have a base of 10 and you want to convert to another base, divide by that number, not the remainder at every point. I'll take one more example there. Just one more example. I want to convert, I've given another one. I've said, what about if it's a decimal, if it has a decimal? It's okay. So let me again do that. I've said, if you're given a fraction or a decimal, a decimal number that has a decimal, that means like if I'm given 0.8125, and this is a decimal number. And then I'm asked to convert it to another base. What we do is we multiply that new base by this number until you get a whole number. You multiply until you get a whole number, and then you stop. For instance, I want to convert this to binary, so I multiply it by 2. What I get is 1.625. So I take this decimal part and multiply it by 2 again. This is what I get. Then take this decimal part and multiply by 2 again. This is what I get. Then take this decimal part and multiply by 2 again. This is what I get. I've reached a whole number. I've reached 1.0. 1.0. So when we reach there, we now write what we got from up going down. We write the numbers before the decimal. We write the numbers before the decimal, that is 1, 1, 0, 1. So this is the binary number. Then put a 0 before that. So that's all we do. This is what we got. So if you are given a decimal number, a number that has a decimal, a fraction decimal number, to convert to another base, we are multiplying and multiplying until you get a whole number. Now, I was to show another example of converting to another base, from decimal to another base. Let me convert to base 8. And base 8, you're calling it octal number. It uses base is 8 and it uses numbers 0, 1, 2 up to 7. So to convert a decimal number to octal, we are again dividing by 8 and noting the remainder at every point. And so 8 goes here 8 5 times, and the remainder is 6. What about 8 into 85? Goes there 10 times, and the remainder is 5. What about 8 into 10? Goes there once, and the remainder is 2. What about 8 into 1? Go there 0 times, and the remainder is 1. So we note these remainders from bottom going up. We get 1,256. So somebody will ask, what about if I have a number, a decimal number that has a whole number, let me say like 2686.25, and I was to convert it to octal. What I will do, I'll convert this part first using this method, and then take this decimal part and begin multiplying by 8 as I go down until I get a whole number. And then I'll combine the two results. So I think I will stop at 2140. At exactly 2140, then as the time I'll stop. Now you'll try this, convert this to octal. I've already said that you just multiplying by 8 until you get a whole number. I've done that, I've found 5. Then when you are doing that, you write from up going down. Write them from up going down. So you have 765. Remember, you are dealing with a decimal number, so you have 0.765 as the new number of base 8. Now, so at your own time, since they are recording, you look at this working, and then is this working where I've converted this decimal number to base 7, dividing by 7 and noting the remainder. So you look at that, and I've also talked about hexadecimal numbers that uses 0 to 16, but now from 10, instead of 10, it's A, then B is 11, C is 12, D is 13, and then E is 14. How many numbers are those? Are supposed to be 16 numbers. So 0 is 0, 1, this is 1 number, 2, 3. So up to here, those are 10 numbers. But now 10 is A. And then B is 11. This one is 12. This one is 13. And then this one is 14. How many numbers are those? Okay.
There are 15
Now,
numbers.
so there are 15 numbers, huh? That are supposed to be 15. I left one out, huh? That are supposed to be 15. Now, so you can also convert hexadecimal number to me. No, you can convert a decimal number to hexadecimal. And we do the same thing at dividing by 16 and noting the remainder at every point. So when the remainder was 11, I wrote B. And when the remainder was 10, I wrote A. And so the new number that I then get is, I write from the bottom, the remainders from the bottom going up. That is AB, 9, then 8. This is the hexadecimal number. Now we can also convert from another base to base 10. And that's what I want to just show, and then we stop at the time that I said. So this one, again, you look at the working here. Now, this is what I'm talking about. To convert a number from another base to base 10, we use the place value notation. What does the place value notation say? The place value notation says, for instance, if I have a number like 345, what is this number? This number is the same as 3 times. The place value of 3 is hundreds. And then 4, what is the place value of 4? Is tens. And then what's the place value of 5 is ones. So 345 is the same as this. So this is the method we use to convert a number from another base to base 10. So for instance, if I'm given a number, yes.
From what you just deleted, the 4 should have a 10 to the power 1. You'd written 2.
Yes, I mean, should be. Oh yeah, look, you can use this example here. So for instance, I have 723. The base, the 10, 7 is hundreds. Then a 2 is a minute. 2 is ones. Then this one, power is 0. So what was your question?
Oh, in the previous example, I think you just mistyped the tens. You'd written the hundreds twice, yes.
I wrote 100 twice, eh? So like this one is supposed to be, then this one is supposed to be 10 raised to 1. Then this one is supposed to be 10 raised to 0. This is okay, is that okay?
Yeah. Yes.
Yes, but so that we have 300 plus 40 plus 5, which gives us 345. Now, so I want to convert this decimal number, this binary number to decimal. And again, we're just using those place values. So this would be 1. We are multiplying by that base. So the base is 2. The base is 2. I want to convert it by 10. So we multiply by 2. And then we just count the place values. So this, what is the place value of this 1? The 1 times 10 raised to what? 1, 2, 3, 4. So times 10, so this would be 4. So the place, the total value of this one is 1 times 4, 1 times 10 raised to 4. Then plus the next one, this one. So its total value is supposed to be 2 raised to what? So 1, 2, 3. So it's supposed to be this one here. This one is the one I'm talking about. Its value is times 10 raised to 3. So that 3 is the one I put here. Then plus the next one times 2 raised to what? So this would be 100, which is 2. Then plus 1 times 2, is it 1 or 0? The next number is 0. Of course, 0 multiplied by anything would be 0. But what is the place value? This would be 1. And then plus the last number here is 1 times 2 raised to 0. Then this one is after the decimal. After the decimal, what we have, the first number is multiplied by that, and the second number is multiplied by that, and so on. But this one is the same as 10 negative 1, and this one is 10 negative 2. So that's what you're seeing here. So this is 2 raised to negative 1. This number here is 1 times 2 raised to negative 1 because of what I've explained here. And this other one is 1 times 2 raised to negative 2. And so the decimal number that you get therefore is this, or the denary number. We do the same thing for if you're given another base and you want to convert to base 10. We do the same thing. For instance, you look at this working later, convert this octal number to decimal. So just it's 1 times 8 raised to 3 raised to 2 plus 5 times 8 raised to 1 then plus 7 times 8. I think I made a mistake here. I used 2 instead of 8. This is supposed to be 8. And then this other one is okay because it's 6 times 8 raised to -1.
Okay.
Now you look at this other example. I've already done the working, just converting from other places to base 10. And then when we meet tomorrow, we shall look at modular arithmetic. And from here, that is now when we shall be looking at the application of what we're doing today. Thank you.
Mwalimu, thank you so much.